Hello and welcome. Today we're going to be talking about computing volumes with cylindrical shells. All right, so recall, we talked about solids of revolution. And these are the kind of shapes you make in pottery class or on a lathe. Okay. And so one way we can think about it, and I'll just show you an example, right? Like, if you were like literally in pottery class, you'd make like some sort of vase or something. You would make a shape like that. And it'd be on a pottery wheel, spinning around or something like that. And then there'd be an axis. Okay. And we talked about, in the last video, we talked about the idea that basically we could basically slice up the solid into little slabs, little disc slabs. So we can write it like this. And each slab goes like that. And of course, as the vase gets broader and broader, our little discs get wider and wider. Okay. And we can continue this up all the way up, right? So in this case, I would integrate from, let's say if that's 0 down there, I'll just say it's this A and this is B. And of course, we're integrating along the y-axis. So we're going from A to B along the y-axis, right? And we'd be looking at this curve right there. That's going to be f of y equals x, right? Because everything's turned over from what we first probably introduced this as, and there's the x-axis, right? So that basically is the x-axis, the width, right? And this represents, of course, the radius of the discs. All right, so with that together, what we can do is basically say that this is going to be pi f of y quantity squared dy. And that would be the volume of that shape. Okay, so that's fine. But it turns out there's another approach to doing these types of shapes. And it depends on the application. So now what I'm going to do is I'm going to talk about another approach. For solids of revolution. Okay, so what is this other approach? Well, we're not going to do discs. Instead, we're going to do cylinder shells. So what are we talking about here? Let's draw another pottery wheel, let's say, okay? And on that pottery wheel, we're going to put, let's use a cool color here. We'll go with purple. And we're going to put a shape, let's say let's make like a bundt cake. So, around there, like that. Okay. Well, that's the shape we're going to make. It's going to be kind of, I'll call it a bundt cake. Okay, so if you've ever seen one of those bundt cakes, in fact, the idea here though is that what we can do is with this shape, if we look at the cross section of it like that, there's the axis, the y-axis. There's that flatness of the thing. what we can do is we can think of the x variable. We know that again is going to be that radius. Okay? And of course, we have some f of x is equal to y. That's going to be the height. Okay? So that gives you that height. So, and we know that the shape that it forms is going to be made by going around in a circle like that, because again, we have a whole nother bundt cake on the other side there. And that forms, we can think of it as forming a little shell, a little cylinder. Like that, okay? Okay, if that's a cylinder, and what we can think of basically is this cylinder is going to have a little thickness. Okay, we're going to say that thickness, of course, is going to be delta x thick. So let me see if I can draw this a little bit better. I'm going to go to another page now. Right, so again, we have this bundt cake type shape. It goes around, goes on the back side. And if we're at a certain point at x, we're going to go up. And that's, of course, going to be y there. And all the way around, we're going to have that cylindrical shell, like so. And it's going to be dropping down and hitting the base of that pottery wheel. Okay? And then it's going to have a little thickness to it. Like that. I don't know if that's the best cylinder I've ever made. All right, and so what is the volume of this shell? Well, we know the radius. That's going to be x, okay? We know the height. The height, of course, is going to be y is equal to f of x, right? Whatever the function f of x equals y, that's this profile of that curve there, right? Okay. That's the height. All right, and we know that basically we can unwrap the circumference. And it's going to be 2 pi times x, that's the radius, times, and I said that there was going to be that tiny delta x is going to be that thickness. This delta x, right? Okay. Times the height. So that becomes this little tiny volume. Okay. And what we're really doing here basically is taking that and unwrapping it. And of course, here is going to be that height, right? And then the length is going to be 2 pi x, right? And then the thickness, that's going to be, I'll do that in blue too. That'll be delta x, right? So one way we can characterize this is the idea is that actually dv is going to be equal to 2 pi x times f of x dx. So that's a small thickness. And that is a small volume. And of course, if we have a and then a B, we know how to integrate it. the total volume is going to be adding up all the shell volumes and the idea here is, of course, is this shape actually can be constructed out of a series of nested shell volumes that are nested inside each other. Okay. So this symbol in itself doesn't do a whole lot, but I think it invokes the thing that we want to do, which is we want to break down that volume into a bunch of little volumes, and to get the total volume, what we're going to do, of course, is add up all those little volumes. But we're going to break that out, and actually it's going to say be an integral now from A to B, whatever the limits of that of the volume is, times 2 pi x f of x dx. This is the explicitly calculatable integral. Okay. All right, so if that's my shape, let's actually now do this exactly. So let's let y equal a minus x times x minus b. And a is going to be greater than 0, but less than b. I'll say a is about there, and I'll say b is about there. And that's going to form a parabola that looks like this. Okay. And this is going to be the x-axis there. There's 0. Okay. Right, and of course this is going to form that bunt cake shape sitting there. So of course what we have to do now is, well, I'm going to FOIL out my equation here, or my function. That's going to be minus x squared plus a plus b, a plus b times x minus ab. Okay, so again, this is that height of the cylindrical shell. And we're going to start at x equals a and go to x equals b, and x is going to move this way. We're going to integrate through to get all those shells as we go around. So the volume, and again this is total, is going to be the integral from a to b of 2 pi times x times the height, negative x squared plus a plus b times x minus a b dx. So now we've built our integral that actually computes the volume of this bunt cake shape. Okay. From here, we can just calculate it, and I'll at least start the calculation. It's not that illuminating, really, but I think it's worth just demonstrating where we're going with this. Right, and of course you can choose A and B any you want. I'll let you figure out which size of bunt cake you want to choose. I just made it so that A was bigger than 0 and B was bigger than A, and you can choose your own dimensions however you like. Okay, so all I did was just distribute the x into each term there, dx, and then go 2 pi, and now we have negative x to the 4th over 4, evaluated in a and b, take the difference, plus a plus b over 3, x to the 3rd power, evaluated a to b, And then, of course, minus AB x squared over 2 evaluated A and B. And from here, it's just arithmetic. I'll spare you the details of how to actually go about this integral. I'll just stop there with this video. We've done an example now of doing a volume with a cylindrical shell. In other videos, I think I'm going to do more examples of various volumes. And then we also want to ask the question, I haven't really addressed this yet, but when is a shell versus disk method best? And the answer, of course, is it depends. But we might see a few opportunities where we could at least say, for a particular shape, what would rule out shells versus disks? And I'm sure if you thought about it enough, you could probably come up with some examples of where a disk would be better versus a shell. But there are many shapes, of course, that would be amenable to both methods. So again, we'll talk about that in a later video. Anyway, thank you very much, and I'll see you in the next time.